This seminar is hosted, or it's sponsored by the Association of Environmental Engineering and Science Professors, AEESP, who organizes a lecture tour every year. And Dr. Elimelech is with us for the tour this year, and this is the first stop in roughly 15 or 16 visits that he will do this academic year, both the fall and spring. So this is a nice event to kick it off. I hope that we all enjoy ourselves. And hosting this particular lecture is, of course, Clemson University and the Department of Environmental Engineering and Earth Sciences, but also we have co-host institutions, the University of South Carolina, both the Department of Civil and Environmental Engineering, as well as the Department of Chemistry is joining with us. And then we have some folks from the University of North Carolina, Charlotte, that have come down, and we're interacting with them. And then also Benedict College, and I lost the Benedict folks. There they are in the background, or in the back. Thank you all for attending and for co-hosting this event. Menachem Elimelech, our speaker, is the Roberto C. Gorzetta Professor in the Department of Chemical and Environmental Engineering at Yale University. And he's going to be introduced in a lot of different ways, perhaps, during his lecture tour. So I thought I would introduce him sort of to help you gauge his impact just with a sample size of 1. So the sample size of 1 is myself. I have been seeing Dr. Elimelech's work since I began graduate school, and I got interested in desalination myself. And the way I can say that first is when I first started looking up papers and literature, my advisor said look at literature, and I started Google, or well, I don't remember if I Googled at that time, I guess so. But his papers popped up, and papers from his research group. One of his students, Eric Hoek, is a professor at UCLA now, and some of his papers led and really are the ones that I studied and paid a lot of attention to and got my equations from to be able to do my dissertation work. And thinking later on, we hired a professor at the University of Illinois named Helen Gwynn, and she had done a postdoc with Minnie. And then one of my my colleagues, another student at the University of Illinois, Baosha Mi, she graduated from Illinois and went to do a postdoc in Minnie's group, and now she's a professor at Berkeley in doing environmental engineering work. And then Amy Childress, just last week, I wrote a proposal, and Amy Childress, or she wrote most of the proposal, I should say. I was a co-PI on a proposal that Amy Childress put together. She is now the chair of the Environmental Engineering Department or program at the University of Southern California, and she was one of Minnie Elimelech's students. And just last year, we had Shihung Lin visit us, who is one of Minnie's former postdocs. And I could go on and on. Many people in the field that we interact with came out of Minnie's group as students or postdocs. And many faculty members have come out of his group. And his impact has been huge in the field. And so, without belaboring the point further, we'll let him tell us about desalination and get us into this topic today. Minnie?
Can you hear me? Okay, thank you, David, for the kind introduction, and I'm very pleased to be here, my first time at Clemson, maybe my second time in South Carolina. And I would like to thank Clemson and the other institutions for hosting me here. And I hope today I will teach you about desalination rather than getting into the very detail, tell you more about the big picture of desalination, where it's heading, is it sustainable, and then while doing so, we'll talk about some more fundamental science. So I would like to start with where I came from. I'm from the environmental engineering program at Yale University. We are part of the chemical and environmental engineering department. We are 6 faculty, as you see here. One of them was the advisor of Ezra, which is a faculty here, Jaehoon Kim. We also have affiliate faculty from the School of Forestry and Environmental Studies and other programs. As you see here, some of them probably you heard about some people here like Tom Gradle and Joe Pignatello. And we cover all aspects of environmental engineering, water, air, soil, and also chemistry, physics, and biology. And this is just a list of topics that we are covering. But before going into my talk, I would like really to thank the people who did all the work. And these are my former graduate students and PhD students, postdocs. And these are some pictures coming from different time from the groups, and I would like to give this quote from the Talmud. Again, you always learn a lot from your teachers, from the colleagues, but really, and I'm saying it really, I learned so much from my students, and I'm continuing to learn so much from my students. So everything that here is really I attribute to my students and postdocs. So let's start now with the technical part of my talk after this brief introduction. And I would like to start with a list of the top 10 global challenges for the new millennium as put forward by Richard Smalley, is a Nobel laureate. He put it together about 10 years. And it's not surprising that you see energy and water in the top of the list. And indeed, if you go over any of these or many of these items here, let's see the laser, they're all somehow related to water and energy. Now, my talk will focus on water, but also a close link to energy, and we can tie it together in what we call the water-energy nexus. I will talk specifically about desalination, and desalination needs a lot of energy. The same way, if you produce energy or power, you need a lot of water, so they are truly interrelated. Indeed, we can extend this nexus to the water, energy, and food nexus. Because as you're going to see very soon, food and agriculture consume most of the water. Over 70% of the water consumption in the world on average goes for food and agriculture. So we put it together into this energy, water, and food nexus. And indeed, NSF has a program related to the energy, water, food nexus to try to make the right connections between these three disciplines. Now, when you talk about water and energy, they are directly related to the new United Nations Sustainable Development Goals. And you can see it through this specific, through what you see here, zero hunger related to food, of course, clean water and sanitation, clean energy, and here you see some clean energy, and here you see some climate change. So all somehow related to water and energy, which is the main topic of this talk. Now, I was talking about water consumption. There is a really rapid growth in water consumption, and it's mainly because of population growth. Indeed, what you see here, and I indicated earlier, agriculture consumes most of the water. You see here exponential growth in water consumption for agriculture, and here you see it for the other industrial section and the domestic section as well. And it mirrors the growth in the population, and the projected water consumption in 2025 will be somewhere here. Now let's talk more about water that goes to food and agriculture. Again, everything that you do today now, when you eat, drink, or you wear leather clothes, all have some what we call water embedded in it, or water footprint. And let's talk about some water footprint of some typical things that we do every day. Again, most of you drank coffee this morning. To get one coffee, if you think about all from the beginning, for the coffee beans and so on, it takes only 35 liters. But if some of you ate this lunch hamburger, it's 2,400 liters of water just to get one piece of hamburger. It's a lot of water that usually we don't think about it when we think about water, because we think about seeing the water flowing and real water. Now, if you eat healthy food, it consumes a lot of water. And now here I will switch from liters to gallons. If you see here one head of broccoli, it's 5 to 4 gallons of water, and so on. Now, I don't know how many of you followed the news about the drought in California. And do you recall what was the evil of all? Almond. I mean, they really were attacking the almond grower because one almond will consume 1.1 gallons of water. So it's clear now that there is a significant increase in water consumption, and the question is how to increase available water supply. We can get a certain amount of water from the hydrological cycle, but nothing beyond it, and it's not enough because we have more consumption than what we can get from the hydrological cycle. So there, where we turn to engineering. Through engineering, if we can desalinate seawater and also recycle wastewater, we can get more water than what you can get from the hydrological cycle. My talk will focus only on desalination, and the key for desalination is really to enhance the sustainability of this process. So I will focus mostly on the sustainability and energy consumption of this process. So let's talk about seawater desalination and what are the main features of seawater desalination. In principle, it offers an unlimited steady supplies of water. The ocean is vast. You will never deplete the ocean. Indeed, it's good that if you will use more water for desalination, you can lower the level of the oceans. I mean, if there be some ice will melt and so on. It also, you can produce water without affecting the ecosystem. If you draw a lot of water from groundwater, it can affect the ecosystem. If you draw too much water from the rivers and lakes, it affects the ecosystem. So these are the two advantages, but of course, there are also disadvantages. Again, you go to the item 3. It consumes more energy than typical processes by a factor of at least 3 to 5 than conventional technologies, for example, just to recycle wastewater or treat water from the river. And also there are growing concerns about the environmental impact of seawater desalination, and both the energy and environmental impact I will address in this talk. So let's start to talk about the technology. The state-of-the-art technology for desalination is reverse osmosis. Although there are some thermal desalination plants in the Gulf country, they are much more energy intensive, and all the new plants that are built nowadays are based on reverse osmosis technologies. Again, there is an intake structure that you take the water from the ocean. There is a pretreatment, sort of similar to the way we treat water for drinking water that you see here. Then the main stage is the reverse osmosis unit that really desalinate and remove the salt from the water. And you also have here post-treatment, which is very important to add minerals and some other things that are mentioned later. And in the end, you discharge the brine to the ocean. So we will get back to this slide when we talk about the energy, the environmental impact, but just note the thickness of this line, which is proportional to the energy consumed by each of these stages. And most of the energy will be consumed to desalinate the seawater and by the reverse osmosis stage. Now, as I indicated, there is a rapid growth in desalination capacity all around the world, and I will give you just examples of some recent desalination plants that were built. One that was just completed this year or last year was the Carlsbad desalination plant next to San Diego. It's 70 million cubic meter or ton of water per year. And it took California 12 years to decide and argue until eventually they built this desalination plant of 70 million gallons cubic meter per year. Israel completed 5 major desalination plants, and these are the 2 recent desalination plants along the Mediterranean. One in Sorek, close to Tel Aviv, and one in Hadera. I was born in this town of Hadera, in Israeli. And as you see, the capacity is huge. Again, each one of them is twice as much as the capacity of the one in San Diego. And Israel built 5 of them. Singapore completed 2 recently, the second one. Spain, and so on. A lot of plants. And of course, as you'll see very soon, there will be a lot of energy consumed through this process. So what I would like in this talk to address 4 major questions. And after going through these 4 major questions, hopefully you will have enough information together to judge if seawater desalination is sustainable or not. I will not give you maybe in the end some clear answer, but I will give you generally my opinion in general terms. And the key questions that we are going to address here are as follows. I will talk about first, what is the current energy efficiency of desalination? So you can see some real numbers and see if it's really a lot or not a lot. Then I will talk about material science. A lot of material science thought, okay, we can really improve the energy of desalination by having membranes with unique materials, and I will address this in the second question. Third, are there any other innovative technology that can really improve the energy efficiency of desalination compared to reverse osmosis? And lastly, I will talk about the environmental impacts. What are the environmental impacts of desalination? So let's start with the first question. And here I will make it very simple. Again, any one of you who took a thermodynamic class, and again, all engineering, I think it's required, you can calculate the delta G of separation, the free energy to separate water from the salt. And again, you assume a reversible thermodynamic process, and this will be the best energy. I mean, you will never be able to do it with lower energy because it's a reversible thermodynamic process. And whatever you calculate here, it's independent of the technology. You cannot come and tomorrow and tell me, I have now a new technology, not reverse osmosis, and I can do it less than the values that I'm going to talk here. You can't, because you will violate thermodynamics. We can't do it. And be surprised, I get sometimes calls and proposals or some smart Yale undergrads, oh, I have a new process, I can cut the energy by 50%. Remember this number. So when you do this calculation for seawater, which is 35 grams per liter, if you take 1 drop of water, which we call it zero recovery, it's 0.76 kilowatt hour per cubic meter. 1 cubic meter is 1,000 liter or 1 ton of water. If you have 50% recovery, we mean you extract 50% fresh water and left with 50% brine, the energy is about 1.1 kilowatt hour per cubic meter. So remember this number, you can never desalinate by any technology less than this value if you have 50% recovery, which is the way we desalinate seawater nowadays. Now let's talk a little more about the energy of desalination and relate it to the process itself. In reverse osmosis desalination, you have membrane modules. Again, some of you here are doing some membrane work, and these membrane modules have a lot of area of membranes, and they are put together in a pressure vessel, many of them, and the seawater enters here. You can think about the osmotic pressure of the seawater here, or the salinity, and as the water goes and you squeeze and get clean water, the salinity of the brine inside will increase, as you see here. Oops. Will increase, as you see here, and at the end of the channel here of this pressure vessel, usually it's about 6 meters, this will be the osmotic pressure. So the theoretical minimum energy that you calculate based on thermodynamics is just the area under the osmotic pressure curve, and this is the equation that you derive. You can relate it directly to the osmotic pressure of the feed water. And all the energy above it, these are the irreversible energy losses, because you need to operate not as a reversible thermodynamic process. You need to have a certain amount of flux, and these are the energy losses. So you realize that to desalinate, you must apply pressure, at least, this is the pressure, at least equal to the osmotic pressure of the exit brine. Otherwise, the water will not go, you will not be able to desalinate. Water will go the other direction. So now we can define the practical minimum energy. As I indicated earlier, the way we operate reverse osmosis with this pressure vessel, you cannot operate with less than the osmotic pressure of the exit brine. Seawater, 35 grams per liter, it's about 27 bar or atmosphere. It means if you have 50% recovery, it will be 54 bar, 55 bar, which is equivalent, if you do the calculation of this pressure, to a 1.56 kilowatt hour per cubic meter, assuming that everything is ideal, the pumps and so on. So the way we operate reverse osmosis nowadays, the way, is one stage and so on, you cannot do it is less than 1.56 kilowatt hour per cubic meter, and this is the practical minimum energy of desalination, because the way we operate the plant in a way that you apply such pressure here. Now let's see what's the energy of desalination just for the reverse osmosis stage in the past 40, 50 years. Reverse osmosis technology was invented, in the 60s, and again, at that time, the energy consumption was huge, was over 15 kilowatt hour per cubic meter. And the energy consumption dropped dramatically, and again, although I don't have more data here, even if I put data, it's nothing changed. It's the same. Now, why we got this improvement in energy? We got much better membranes with much more higher permeability. We introduced pressure exchangers in which you can recover the pressure in the brine rather than release the brine, the pressurized brine. You can recover it. You have more efficient pumps and so on. Now, this line that you see here, this is the thermodynamic minimum energy of 1.06 that I mentioned earlier. Now, although there were significant reduction of energy in the past 50 years, if you look what's happened in the past 10 years, there were no improvement in the energy consumption of desalination. It roughly stays the same as you see here. And again, I told you that all the other data doesn't, again, this is just, it's not lower than this. Let's zoom on this part. This is the 1.06, the theoretical thermodynamic minimum energy that you will never be able to do it below. The current reverse osmosis stages in the most modern desalination plant, they consume about 2 to 2.2 kilowatt hour per cubic meter. And this is the minimum, so there is some room for improvement, but again, it's not that you can save dramatically energy by reducing it by 90%. So this was, and I mentioned earlier, just for the reverse osmosis stage. Of course, desalination involves intake, pre-treatment, and post-treatment. And currently, the current plant, the most modern plant, consumes between 3 to 4 kilowatt hour per cubic meter. The one in Israel consumes 4 kilowatt hour per cubic meter because they use the water for agriculture, and they need to remove in the post-treatment boron and chloride. And to remove the boron and chloride, they need to have more reverse osmosis stages, because boron is not rejected well by a reverse osmosis membrane, and chloride rejection, although very high, but you start with such a high value, it's still in the product water you can get a high level of chloride. So they do 1, 2, and many times 3 more stages, and this is why the energy of desalination goes all the way to 4 kilowatt hour per cubic meter. So remember these numbers. So this was the first question. What the energy efficiency of desalination? Remember the 1.06, the minimum, thermodynamic minimum. You will never ever be able to do it below unless you develop new thermodynamics and so on. And remember the practical minimum energy nowadays is 1.56. Now let's talk about novel materials. I know material scientists always try to find some new areas and new fields to get in, and a lot of them got to the area of desalination, and they promised, they said, let's have high permeability membrane with high water permeability, and they promise a quantum leap in desalination. And there are many smart people that are going to do it, very top-notch physicists, and naively they thought, if you have more higher permeability, you will need less pressure, and if you need less pressure, you need less energy, because the energy in desalination is just the pressure that you apply. And there were plenty of studies, and again, they resulted in top papers in Science, Nature, and so on. They thought about carbon nanotubes, and they found that carbon nanotube, the water flow there is very, very high because of it's hydrophobic and smooth, and the water goes through just one file of water with no, again, the no-slip boundary condition doesn't hold here. And they promise really that this may be revolutionize desalination. Aquaporin membranes, also aquaporin, again, the protein channel, and I will talk about them later in the talk. They can transfer water at high rate, and people thought if you can incorporate them into membranes, you can increase the permeability and save energy. And the same with graphene. It's, again, the novel materials, maybe in years and other materials. And they did some molecular dynamic simulation and showed that graphene, because it's very thin, atom thick, the resistance is very, very low, so you can really have a desalinate water that's suggested with low energy. Now let's go about this again. Whenever you have anything in the published in Science, Nature, the news coming into it and so on. I would like to show you just anecdotally. How many of you see the Late Week Tonight by John Oliver? Anyone saw it? This one? So they talk about, you hear about things, and the scientists publish something about coffee can do such and such, and if you eat chocolate, you will do, and then they extend it. Similar things were done in desalination. I would like to talk about the graphene. Lockheed Martin, it's a very respected company. We use their airplanes all the time. They did some molecular dynamic simulation of 1 atom thick graphene, and they said we can have some pores there. Again, computer can do anything. And they said there will be very high permeability, and they wrote something that really, it can do magic. I don't think they talk about really the energy saving, but what the media did, the media jumped and said you can save 99% energy. Again, I showed you the thermodynamic limits. So this is really when you have these kind of hot papers and the news are extended, and I don't know how he got to 99% energy. So this is news from, so my point here is that it will not be the case, because energy is governed by the osmotic pressure of the brine. The membrane resistance doesn't play a critical role. The thermodynamic of the brine play a very important role. I already mentioned that the osmotic pressure of the oxide brine is twice as much as seawater, 55 bar. So you cannot operate less than 55 bar, even if you put a membrane with zero resistance. So, and what we have nowadays we really operate, again, we cannot apply exactly pressure equal to the osmotic pressure of the brine. There are pressure losses as water flow in the channel. There is a concentration polarization. Usually we apply 10 to 20% more, and the current membrane, state-of-the-art membrane that I'm going to talk very soon, thin film composite membrane, already work in this range. So this is the way we operate reverse osmosis nowadays. The reason why we got this dramatic decrease from 1970 to 1980 was because the membrane before 1980 were cellulose acetate, very, very high resistance, and once they developed the thin film composite membrane, the permeability is not an issue anymore. So we can do, again, this was just intuitively to explain, but I can show you just, we did some rigorous numerical simulation modeling of a reverse osmosis membrane with all the flow in the 6 pressure vessels, and we calculate the specific energy as a function of the water permeability coefficient of the membrane. Thin film composite membrane have a permeability between 2 and 3 LMH per bar, this unit. And as you see for seawater desalination, when the permeability is lower, this was in the early 70s, you can really improve the energy. But once you reach to this permeability, there's hardly any change. Because the membrane resistance doesn't play a role, it's more the thermodynamics that control it, the osmotic pressure of the brine. So this is about membrane materials. They will not improve the energy of desalination, but we will get back to these membranes, and you see that we can use them for other things, and I'm going to elaborate later. Now let's talk about the current membranes. The current membrane, the state-of-the-art, are thin film composite polyamide membranes. Since the development of this membrane in 1980, many companies, scientists tried to come up with different chemistry, and no one can get a better one. Thin film composite polyamide is the chemistry that we use, and no one can beat it at this stage. Now, thin film composite polyamide membrane, although they can provide the right permeability and selectivity to get the energy, as I indicated earlier, they are relatively hydrophobic. They have a rough surface because of the interfacial polymerization reaction that results in a very rough surface. They contain carboxyl group. They're also sensitive to chlorine. You cannot just clean it with chlorine or disinfectant to destroy biofouling. And because of all of these reasons, they are prone to fouling, organic fouling, and biological fouling. So what I'll argue, and I argue it in a review article we wrote a few years ago, is really you can really improve many aspects of desalination by developing a fouling resistant membrane, because the way we operate nowadays in reverse osmosis plant, as you get fouling, the resistance to flow increases, so they increase the pressure because they want to keep the water productivity constant. And when you increase the pressure, typically by 10, 15%, it's 10% increase in energy. So if you can develop membranes which are fouling resistant, it will help in this aspect of the energy. And again, a fouling resistant membrane can improve the reverse osmosis energy efficiency, can reduce the use of chemicals for cleaning, and also can reduce pretreatment energy and cost, because nowadays we need to have a very extensive pretreatment, otherwise the membrane will be fouled dramatically. Again, the plant that some of you heard about in Tampa Bay, Florida, the pretreatment did not work well because they tried a new process, and for 3 years the plant did not work because it was fouled. Whenever they operate the plant, immediately the fouling occurs. So you need to have, if you can find fouling resistant membrane, you may reduce the pretreatment. And I would like now briefly just to tell you some of our research activity, how to make the membrane more resistant to fouling. In this case, organic fouling. Again, as I indicated earlier, the membrane is hydrophobic, and organic matter in water and seawater is hydrophobic. It likes to attach to the membrane and foul the membrane. So we developed some ways to make the membrane more hydrophilic For example, this is the thin film composite membrane. We found a way to bind some ligands to very small silica nanoparticles. And once you have these particles, they are very hydrophilic. Because of the positive charge that you have here, it binds irreversibly to the membranes, because the membrane has a lot of carboxyl group, which again, they are not good in terms of fouling. The carboxyl group can enhance organic fouling. And in this case, we were able to get super hydrophilic membranes, and we got much less organic fouling, and I will now show you some data. But anyway, this is one approach. You can do it with nanoparticles. You can do it by just polymer brush layers. We all know that, again, Zwitter ionic polymer brushes or any hydrophilic brushes can prevent organic fouling in many biomedical devices. Indeed, if you have contact lenses, they cover with some kind of hydrophilic polymer brushes to prevent bacteria adhesion that can cause infection. Many medical devices. So we can adapt it to membrane processes. And in this example, I'll show you a recent work that we take a Zwitter ion monomer here. And we use a well-known technique, ATRP, polymerization technique, to bind it. Again, we have some, through dopamine chemistry, we bind an initiator, and we put in the right thing for the polymerization. This monomer polymerize, and we can get this polymer brush layer, which is very hydrophilic, and it's Zwitter ionic, it's neutrally charged. This is just an example. The contact angle of the control membrane was 74. After modification with Zwitter ionic polymer brushes, it dropped to 21. We studied the adsorption of protein to the membrane, fluorescence tagged protein. You see the control membrane, all the membrane was covered with protein, the fluorescent green. The modified membrane, we did not see any protein stick to it. So you can improve the resistance to organic fouling through a hydrophilic modification. We also found, we have some work on graphene oxide, and we found that graphene oxide is antimicrobial, can really kill microorganisms by mechanisms that involve chemical and physical interactions. And we were able to find, again, a way to bind this graphene oxide irreversibly to the membrane, taking advantage of the carboxyl group that you have in the membrane. And once we bound this graphene oxide and we did some biofouling test, we found that the membrane has much less biofouling. When it comes to biofouling, I can tell you that there is no way in the world that you can prevent biofouling, but as long as you reduce the rate of biofouling, it will be a major improvement. Okay, so this was question number 2. So again, membrane materials will not improve the energy of desalination because it's not controlled by the resistance of the membrane. Fouling may help, fouling resistance membrane may help, as I showed earlier. So let's go now to the third question. Are there innovative systems and technologies that can reduce energy demand? And I can show you through some system approach, process engineering that any chemical engineer can do. You can really improve the energy of desalination significantly, and you don't need all these membrane materials, carbon nanotube, but unfortunately, this is not a very attractive area for researchers to publish on process engineering. Everyone wants to do paper in Science, Nature, get tenure, be famous, and so on. But we can do it very simply. Let's take an example. I showed you the way we operate one stage. If you operate just 2 stages, if you take the brine from the first stage and pressurize it, go to the brine here, schematically, if you remember these are all the irreversible losses. If you just pressurize it, it gets certain recovery by the first stage, and then go to the higher pressure to the second stage, you will save this amount of energy. If you do the calculation, for one stage, I told you the practical minimum energy is 1.56 because you need to apply pressure equivalent to the osmotic pressure of the exit brine. 2 stages is 1.28. Anyone who took chemical engineering classes or any CS, if you have many CSTR in completely mixed reactors in series, you can approach the plug flow reactor. Same way, if you get infinite stages, you can approach the minimum energy of desalination of 1.06. Now, membrane companies know it, and just by putting 2 stages, they can easily save 20%. But although in academia we talk about energy, and we need to educate people that energy is important, membrane companies and utilities, they worry about the cost of the water. Adding another stage will increase significantly the capital cost of the plant, and it's not acceptable by them. Now, we can do some analysis. And this was work by Xiong Ling. You mentioned he came here to visit, and probably he presented this work. So you can just have n stages in series. You can work on the mathematics here. I showed you the example of 2 stages. And when you work on the mathematics of n stages in series, you recover the equation of the Gibbs free energy of separation, exactly the same equation. So you can prove it mathematically by infinite number of stages, you can approach the minimum energy of desalination. Now, I showed you that you have more stages, you can reduce the energy. Again, the idea is if you can really find a way to ride on this osmotic pressure curve. So I would like now to show you a very innovative approach by an Israeli startup company again. And it's called closed circuit desalination. Rather than having physical stages that increase the capital cost, they do what we call operational stages. And the way they do it, they have the feed water comes here, and then you circulate it here and squeeze the water. And as you circulate and fresh water coming out, the salinity increases. And then you bump the pressure again, circulate, and when the osmotic pressure goes up, you bump the pressure again. So what they do here, instead of physical stages, they do operational stages, and indeed by doing so they can cut the energy significantly. When we did it initially, we were surprised we did not recover the Gibbs free energy of mixing, because it's not exactly reversible thermodynamic process, because here we always get some feed water that mixes here, and we have a mixing here. So whenever you have mixing, it's just it subtracts the energy. So, but we get very, very close, and I will show you here. So again, this is just the process of closed circuit desalination, and let's compare it to one stage RO, which is the typical RO that I showed you earlier. That minimum energy 1.56 and so on. If you do 2 circulations, like 2 operational stages, you can drop the energy by 12.5%, which is very significantly. If you think about the major, the capacity of desalination in the world, 12% translates to billions of dollars. If you do 4 stages, you have 18.5, and if you do the practical thing, like this process does easily can do 8 stages, you can save 20% energy. And again, it's an engineering process, very ingenious the way to think about it. The company now apply it mostly for brackish water, and maybe in the future they will also go to the desalination market for seawater. So this is the third question. I showed you that through some system design that you can learn in any basic chemical engineering classes, you can improve the energy of desalination, but it's not attractive for research, but it's very, very useful. Now let's go to the fourth question. What are the environmental impact of seawater desalination? So let's see, I'm okay with time, yeah. So let's bring you again the diagram of desalination. And what's the interaction of desalination plant with the environment? First one is the intake. You intake some water, you may affect some aquatic organisms in the ocean. Second, we see here that we have a power plant that provides electricity, and again, CO2 emission, it's energy. And you can also have here the discharge of the brine. So we can summarize it here. For the intake, one of the big issues is what the impingement and entrainment. When the way you have the intake structure, they have a screen, and you have a lot of larvae and other small organisms that stuck in the screen. And in California, they were fighting for it for 12 years. Because of this, until they have some regulation now that in California you cannot have a free intake. You need to dig the intake in the dunes, and so the water will go through the sand, and to minimize and prevent this impact of the impingement and entrainment. Greenhouse gas emission, I will show you some calculation. Again, if you know the energy, you can calculate how much CO2 will be released, and you'll see that the number is quite high. And brine discharge can impact marine environment, and again, you can minimize it by locating the desalination plant in an area that there is a lot of mixing, and also you don't discharge it directly close. You have a pipe that goes far away, and you can minimize it. So these are the environmental impacts, and I would like just to give you an example of again, just some calculations. So let's talk about the gas emission. This is the major concern, really, the energy of desalination, which is very high. And again, at least people claim very high, and I'll put everything in perspective in the next slide. So existing plant can go all the way from 3.5 to 5. Some of the old ones go to 5 kilowatt-hour per cubic meter. So you can, the way you make electricity, you can show that the calculation is that, knowing the kilowatt hour here, you will have 1.6 kilograms CO2 released per cubic meter of fresh water. To get a cubic meter of fresh water, you need this energy, and this will be the CO2 emission. Now let's take an example in Israel. The capacity nowadays is 0.65 billion cubic meter per year, which translates to 2,600 gigawatt hour per year and 1 billion kilograms CO2 per year. If you do the calculation, it can be translating to adding, many kind of, I don't know the number, probably close to 100,000 cars, equivalent to the emission that come from many cars, like tens of thousands of cars. So it's quite significant, and when in the end, when I conclude about the sustainability, I will comment on it more. Now let's put things in perspective in terms of energy. So again, let's take an average, desalination plant at 3.5 kilowatt hour per cubic meter, and remember the RO, reverse osmosis stage, is only 2 kilowatt hour per cubic meter. Let's look at some other ways, other water projects and the energy involved. In California, we bring the water all the way to Southern California. Again, I used to be at UCLA, and we get all the water from Lake Shasta going all the way through the Sacramento Delta. And the energy to go through all these aqueducts and going over the mountains, it's 2.3 kilowatt hour per cubic meter, almost close to a seawater desalination plant. Southern California also take water from the Colorado River, and it's shorter distance. It's only 1.6 kilowatt hour per cubic meter. Just as perspective, if you desalinate or reuse wastewater by the most advanced technology that involve reverse osmosis, you can get water with only 0.9 kilowatt hour per cubic meter, just to get everything in perspective. Water treatment consume, I don't know, less than 0.5, maybe 0.1, 2, 3 kilowatt hour per cubic meter, typical water treatment. Now let's go more about things that you do every day. So to get 1 cubic meter, you need to burn 0.6 kilogram of oil to create the electricity. With this fuel, 0.6 kilogram, that you can desalinate 1 cubic meter or 1,000 liter, which is 2,000 bottles of water, of each 1.5 liter. It's equivalent to driving in the city only 2 to 9 kilometers. So it's very, very little. So just think about it. You drive to work every day, 20 miles each way, 40, and how much energy and how much water you could have desalinated. And also, if you operate this energy to get just 1 cubic meter or 1,000 liters, equivalent to operating your air condition in a single room just 1.4 hours. You remember when you go to hotels sometimes and you check in late at night and you go there and they turn on the air conditioning in the morning and it's 60 degrees Fahrenheit. Just think about how much energy and how much water you can desalinate. Okay, so these are the first question. Now I'd like to go and talk about more inspiring for the young scientists. Where do I think the research is going? And then in the end, I will try to answer the question, is seawater desalination is sustainable? So let's talk about what's next. And just to remind you, this is the entire plant. And as I told you earlier here, the post-treatment is very, very important process because current reverse osmosis technology, although it works well, the rejection is not perfect. You get 99.8% rejection or whatever. It's still not enough. And boron is rejected only at the rate of 80%. So as I mentioned, in many places they have 2 or even 3 stages of reverse osmosis that add at least 1 kilowatt hour per cubic meter. Now let's talk about the membranes, how we can improve it. And I would like now to talk about the current membrane, what are the limitations, and where I think the future will be for membranes. Current desalination membrane, like the thin film composite membrane, are constrained by what we call the permeability selectivity trade-off. This is data for one of my former students that showed the salt permeability of reverse osmosis membrane versus the water permeability. Again, we want high water permeability and low salt permeability. But the problem with current membrane, I mentioned the example of chloride and boron. The membrane company can tweak the membranes and improve the rejection of boron from 80% to 95%, but then the water permeability will be very, very, very low. So the energy of desalination will increase because we have this trade-off. If you want to get more permeable membrane, you will sacrifice and more salt will go through the membrane. So this trade-off really, limit us, and we really need a new, just a second, drink here. We really need a new paradigm for membrane fabrication to overcome this limitation. Now we'll talk about it. Now, here I presented it in a simple way. It's more common to present this permeability selectivity trade-off by presenting the water permeability over the salt permeability, which means how much the membrane is selective for water compared to salt. We need a high number, so you will have water going much more than salt as a function of water permeability, and the data that I showed you earlier in this presentation falls here. It's more like a trade-off. So the question now, if we want to design membranes, how should we design it? Should we increase, again, this is currently where are the membranes, should we increase both water permeability and salt, and should we increase both A over B, or just the water and the water permeability? Should we go in this direction, just increase water permeability, or should we increase only the salt permeability? And we did an analysis in a recent paper just focusing on the energy, and again, this is the selectivity, how much, that you let water go more favorably than salt. You need to have high value, and this is the water permeability, and the data is like this. And I showed you earlier, if you go this way and try to get high permeability membrane, it will not help because I showed you it doesn't improve the energy of desalination. So we argue that really future membrane should really, really improve the selectivity. In principle, if you have a membrane that completely selective to all solute and only water goes through, you can save just in the reverse osmosis plant the entire extra passes that amount to 1 kilowatt-hour per cubic meter to remove boron and chloride. In wastewater, we use reverse osmosis a lot in wastewater. It also, you can remove many, many solute that go through a reverse osmosis membrane. And I'll show you here. This graph describes the rejection of reverse osmosis membrane as a function of the molecular weight. For salt, there is no problem because ions are hydrated and are very big, and you see the open symbols are the salt. You get very high rejection for ions, so you can remove salt very well. But when you have low molecular weight solutes or uncharged neutral solutes like boron or urea or NDMA, which is this refractory byproduct, the rejection is low, you see here, and it's a function of the molecular weight. The lower the molecular weight, you get very low rejection. This can be a major problem in wastewater reuse, because when you recycle wastewater, the last stage is reverse osmosis, and all of these toxic chemicals, low molecular weight, can go through, and you need to add another 1 or 2 barriers to prevent them. So if you can really have a membrane that rejects everything, will be great. And here we discussed this issue in a recent review article that you see here, and we talk about future membrane that can really achieve high selectivity. So what we are trying to highlight, and again you saw it from the title, the heading of the previous slide, what's really, really important is the selectivity of the membrane, not the water permeability, because the current water permeability of membrane is good enough. It will not improve the energy of desalination. And in this paper we discuss Aquaporin, I will tell you more about them, carbon nanotube, and some other synthetic channels and graphene oxide that I mentioned here. The most promising one, or the one at least that we did the most work, are Aquaporin and carbon nanotube, and I would like to say a few words about them before concluding my talk. So let's talk about Aquaporin. Aquaporin, again, it's an amazing channel of millions of years of evolution that let water go through. And again, it's a it's a unique structure with you have a region here with only 2.8 in diameter. There are a lot of proteins there, functional groups that can cause some interactions. And eventually they let some aquaporin, like aquaporin human one and also one that you can get from bacteria, can let only water go through. So it has relatively high water permeability. Some aquaporin, like the one that I mentioned earlier, can remove all solute, including, very, very small solutes, like what I mentioned, boron, urea. And indeed, some research showed that, and again, that this aquaporin can also remove ammonia, which is almost the same molecular weight as water, and oxygen because of hydrophobic interaction. It's more hydrophobic than water. So in principle, there are aquaporins that can let only water go through. The question is how we can translate them into membrane. And it's a lot of ongoing research in this area. And the research that was done in this area all now is limited mostly to the vesicle stage. You can incorporate aquaporin into vesicles and study the permeability of water and salt, and they showed relatively promising results. The key is how to incorporate this aquaporin in a planar membrane in large area. And if it's done, and we are now doing some work, I have a student working in this area, we have some ideas how to do it. If it's done, and if the background, usually you incorporate them into a bilayer, either a biological bilayer or just synthetic polymer, black copolymer. And if the permeability of the polymer or the matrix will be very, very low, and you incorporate the aquaporin, it will be a major breakthrough. So this is, I think, quite promising. Also, there was a lot of work on carbon nanotube, but as I told you earlier, they were misguided. They highlighted carbon nanotube mostly because of the high water flux, but I showed you it doesn't do anything to desalination. But I think if it can be done right, if you can use carbon nanotube, you can use them as a membrane that can practically reject everything. Now, I did not mention earlier, but the membranes, the studies on the carbon nanotube showed very little salt rejection, almost nothing. Mostly just focus on the water permeability. So carbon nanotubes are highly permeable to water, again, and can be, in principle, highly selective to solute. If you can make the inner diameter less than 0.4, it can remove all salt, for example. And if you make it smaller, which is very difficult for carbon nanotube, maybe remove some boron, or maybe you can functionalize the interior of the carbon nanotube to mimic these functional groups in the aquaporin. That, again, the separation in aquaporin is really also based on interaction with the groups. But the question is how you vertically align this carbon nanotube. I work with a professor in my department. We tried it. We were able to find some mesophases that you can sequester this carbon nanotube. And this professor, Chinido Musuji, is strong on this magnetic alignment. He's a very sophisticated magnet. We were able to align the carbon nanotube, and then once you align them, you polymerize the matrix, and we got a very nice film. But unfortunately, we were not able to get anything going through the membrane because the carbon nanotube probably was, maybe the density was not high, and they were just not open. So we still work on it, but very, very low, not a lot. And one of my former students, I think I did not go to the Gordon conference, but Robert McGuinness has a company that tried to commercialize carbon nanotube, and he told me that he was able to get now 50% rejection. It's good. But again, unless you get more than the current TFC membrane of 99 point something, it's not good. You need to have perfect rejection. Okay, my last slide. So I talked about these 4 questions, and then for the young scientists here to inspire them where the research can go. And let's now try to answer the question, is seawater desalination is sustainable? I will not give you a clear answer, but this is my opinion that we summarize in this review article. So let's read it together. So although several options currently exist to augment freshwater sources, including treatment of low quality source waters, water recycling and reuse, and water conservation, these options alone will not be enough to meet this need. So there is, need more. So give it some, a little open that desalination may be okay. While seawater desalination must be considered after all other options have been implemented, it should be viewed as a crucial component of the portfolio of water supply options. Like anything in life, you need to have a portfolio of water supply. You cannot have all the water come from one source. You can have some from groundwater, from surface water, and some from desalination. But what I advocated here, you need to try all other options. I mentioned that reuse of wastewater, you need only 0.9 kilowatt hour per cubic meter. So if you try to overcome this public perception that I will never drink a recycled wastewater, and recycled wastewater is very safe. And in California, they're trying to push it very dramatically. So you need to go through all options, including wastewater, because it's much less energy intensive, and before going to desalination. And lastly, for water scarce countries that already implemented all other measures for freshwater generation, desalination may serve as the only viable means to provide water supply. In the example of Israel, they also waited a long time before building the desalination plant. In Israel, they recycle over 95% of their domestic wastewater, used mostly for agriculture. And they can get a certain amount of water from the Sea of Galilee, and which already, very low level. So they really use all the options, and in their case, desalination is justified. In California, I think it's something in the middle. I think they can manage with, if they recycle the wastewater, they can still manage. Other countries like Saudi Arabia, they have no choice, the Gulf countries. But many other countries, for some reason, trying to get to this desalination technology almost to show that we are really very advanced technologically, more like having a nuclear capability. And again, they have many other waters they can treat before going to this very energy-intensive process, which I told you can go all the way to 4 kilowatt hour per cubic meter. If you take the water from the lake, what's the name of the lake that used for water in Greenville? Whatever, they treat it, you need no more than 0.2 kilowatt hour per cubic meter. Compared to 4, it's a huge ratio. Anyway, so I think I'm concluded here, and I would like to thank again the various funding agencies and students for many generations. And you will recognize some people here. Megan Maurer, you met her in the Gordon Conference. Helen Wayne from Illinois, one of your colleagues, and many other people here. So thank you very much.
Okay, I would like to compliment you for a wonderful talk.
Oh, thank you.
I'm not one of these group who are here, but I'm an electrical engineer.
Okay.
Two things I would like to mention to you. One, you were very fascinating. Some of these numbers I've been looking for a long time, but unless I do my own research, could not find it. So
which
what
number?
is the energy consumption?
Yeah.
1 kilowatt hour theoretical and 4 is practical, somewhere in between all the rest, Now what is happening, the disconnect you have, and I think you need to connect to the real world. The solar energy is the only one, and combined with wind, which is sustainable. So you don't have to worry about this whole carbon emission issue. Because world, if there has to be sustainable, it's not going to come from nuclear, it's not going to come from coal, it's not going to come from natural. So don't worry about that issue, about the concern you had. Its second point, take it out. Carbon emission is not the problem. The world will adopt it, and that will be solved. I did thumb rule calculation based on the Israeli number. They are consuming 2.6 gigawatt per year. That's the electricity. I don't have the number for Israel. I know about US number, but let's take 10 penny per kilowatt hour. Then their bill will be $260 million per year. We know today solar electricity can be done at 2.91 cent per kilowatt hour. These are real number. The number will go down further. So, yeah. Plus, you did not go into details of the chemistry, what exactly where the process is going, what steps are.
Yeah.
But I did see one diagram, and I have some touch base with David. He's my kind of mentor in this business. You are using pumps, and if you don't use them as AC pump, but use them as DC pump, 30% of the energy you will be saving. So if I take solar number, which is 2.9, and I cut down the 30, that $260 billion will be $15 million.
Oh, yeah.
And that's the kind of innovation this industry needs. What in solar we have done, we know in 1976, when I was a PhD student, I did my PhD in solar cells. The cost of 1 kilowatt used to be $77. Today it is 40 cents. Why it went there? Because of the manufacturing. So we have a graph. If worldwide I have this much production, next year I'm going to double, my cost will go down 24%.
Yeah,
Same thing happening to the batteries. So I think you guys have to look the whole, and you're such a distinguished person, member of National Academy, you can change the whole world. Look it from the manufacturing side. These guys will get their PhD, don't worry about it. They will get their carbon nanotube, but purely from the world needs leadership from US. And I think that's what
I think you're right. I mean, in principle, if you have everything solar energy, then we don't have this problem. But nowadays, the solar energy is a very small component of the...
It is not. It is growing faster.
I know. I agree with you. But anyway, nowadays, even though you cannot use solar directly, you have solar energy, you create electricity, and then you feed it to the grid, and then you take the electricity from the grid. So I do not disagree with you, but we are still living in the fossil fuel area, and even the prediction that even 50 years from now, still the fossil fuel will be at least 60–70% of the energy consumption. If everything will be solar, you're right, but it's not there.
Okay, this is a good discussion. I think Peng has a question in back, though.
Thank you very much for the wonderful speech. So my question is, could you comment on the hydrodynamic aspect of a memory module design rather than thermodynamic? Thank you.
Okay. Yeah. I think there are some ideas to improve the module design by putting better spacers that can reduce fouling, or now they're moving to a very big diameter module, 16-inch rather than 8-inch, but this will not improve the energy of desalination. They will make the process maybe less. You can improve fouling resistance by better hydrodynamics, but these will be just marginal improvement. There will not be any dramatic things.
How important in reducing the overall cost is the membrane lifetime? So if you were to make a membrane that was significantly more efficient, but it only lasted 1 year as opposed to 5 years or more.
I think good question. The membrane manufacturer guaranteed the membrane for at least 5 years, and the membrane component for the overall cost of desalination is about 4%. It's not negligible, but it's very small.
Okay, over there.
Thank you for your talk. I'm an environmental toxicologist, so you'll excuse the maybe ignorance of my question.
Can you speak up?
It's less. It costs less energy to desalinate water with less ions in it, right? So like a lower salt concentration is less energy favorable. Could you recycle some of the fresh water back into that salt and brine water to reduce the energy? Can
you recycle?
Yeah, recycle some of the water that's pulled out through the fresh water back into the system to lower the molarity rather of the.
But how can you recycle which one? What
just
you
really
left,
bring it back into
you're left with a concentrated brine.
Yeah.
So if you recycle it, you will increase the salinity. It's not a good idea.
We'll recycle the fresh water into the water you're pulled in.
Oh, okay.
Yeah, or is that energetically infeasible?
I mean, you see, if you have available fresh water, significant amounts, so you don't need desalination. So, I mean, you suggest to dilute the seawater by fresh water, but usually you need a large quantity, and if you have already fresh water, why to desalinate? But there are some ideas, and using a process that's called forward osmosis, that you take wastewater, and then by osmosis, if you, on one side of the membrane you have wastewater, the other side the seawater, the clean water will penetrate and dilute the seawater so you can get less energy. So this is the closest to what you are trying to say. So people thought about it, yeah.
I had a question for you. It was a really good talk you gave, but one thing I was kind of waiting to hear was, how does the energy consumption compare between reverse osmosis and distillation of water?
You're talking about by a factor of 5 and 10, it's dramatically, it's no way to compare. I mean, the most effective thermal desalination, multi-effect distillation would be at least 3-4 times more than so it's well accepted nowadays, and everyone know and argue that reverse osmosis is the closest one that you can get to the thermodynamic limit. So thermal processes, those of you who are chemical engineer know that inherently it's not efficient. You are limited by the Carnot efficiency. So the answer is dramatic change. And
so as you're concentrating the salt in the brine, you're also concentrating some of the organic pollutants that were already in the fresh water and the wastewater. What do you do with that brine once you're done with the process?
yeah, when you do seawater desalination, again, you desalinate sea. So in the sea, there are not many toxic organics. You swim there, but there are some chemicals that are used for the pretreatment will be concentrated. So what you do in seawater desalination, you discharge the brine at least few kilometers from the shore. So we think that by the right fluid mechanics and mixing, it's not a problem. However, there is another form of desalination that you desalinate brackish groundwater, for example, in El Paso, Texas. And this is a major issue there. Once you get this brine, you don't know what to do with it. And what they do nowadays, they have deep well injection, the same way that they do now with the frack water. And those of you listen to the news, I was thinking about a week ago or 2 weeks ago was an earthquake in Oklahoma of 5.1, and it's attributed to this putting injection in deep in the groundwater. So for the ocean, there is no problem, although environmentalists, think that it's a major disasters and so on. But I don't think it's a major problem.
Hi. Thank you for your talk. You talked about the trade-off between selectivity and permeability.
Huh?
You talked about the trade-off between selectivity and permeability, and you talked about how we can go towards more selectivity to increase efficiencies in RO.
I can't hear. I think can you speak up?
Oh, okay. You talked about the selectivity and permeability trade-offs and how we can move towards more selectivity to increase the efficiencies of RO. I was wondering, given the emergence of new contaminants and like looking at boron and other contaminants, will there be a commercial viability for less permeable but more selective membranes that have efficiencies that are less high flux?
I think it's a problem because currently the current membrane, they are just in the right range of water permeability. If you reduce it farther, you will need to put more energy for desalination. So, and when you go to a brackish water desalination, the membrane are more permeable, but also if you reduce the permeability so you can get more ejection, you will need more energy. So unfortunately, we cannot win them both. So we need to have something that's completely selective and break this paradigm of permeability selectivity trade-off that is inherent of the separation mechanism of this membrane, which is more solution diffusion mechanism. We need something that's based on unique like aquaporin or size exclusion like carbon nanotubes here.
Okay, some of us could talk about this for a long time, and I'm one of those. But let's have maybe 2 more questions. Go ahead and ask yours, and you can have the final question, Amir.
Historically, people have been making salt, sodium chloride, out of seawater. So right now, is there any industrial interest to couple that process with desalination?
Making salt? Yeah, I think, as you go farther, when you have very, very briny and highly concentrated salt, if you want to extract more water, the energy is intensive, huge. And I don't think and the cost of salt is very, you cannot make a lot of money. So it's not, economically, it's completely not viable. It's just not viable to further, the energy of desalination is proportional to the salt concentration. If you want to further desalinate and get more recovery, you need a lot of energy and cause a lot of problems, so it's just not beneficial.
You mentioned in one of your earlier slides that one of the UN goals is, taking care of the water problems.
UN, United?
The UN, yeah. Was that?
Yeah, United Nations. Okay. Yeah. Okay.
So, desalination, I think, is something that I guess you would consider like a luxury, the Rolls Royce of water treatment, essentially. So, do you think that it's a suitable technology to address these problems in the future?
No. I just show it because they talk about water and we talk about water supply. Desalination will be the very, very last resort, and especially all these developing or poor countries, it's not for them. Okay.
Well, I want to make one announcement real quick, just to make sure. We want to take a picture with everyone who would like to come up first, and then we're going to have the faculty that we're going to send this picture home with Dr. Elimelech. But let's thank him right now, and appreciate your lecture.